Welcome everyone to this session. My name is Ibryam, and I am actually super excited to be in Istanbul for the first time, meet some old friends and make new ones. This will be a high-level talk where we will look at the evolution of applications and where Dapr fits. And I want to start with a question. Who here is using cloud services like Amazon? Amazon services? No. Who is using Kubernetes? All right, that's better. And the last one, who has heard Dapr, the project Dapr in CNCF? All right, looks good. I'm product manager at Diagrid, where we are building services for developers. Before that, I was consultant architect at Red Hat, where I have worked with most Red Hat middleware Java technologies, such as Apache Camel, ActiveMQ, Karaf, Service Mix, all of the Apache projects. And I have a book about it. Similarly, I've used Kubernetes, and I wrote a book about it. If you go to the URL provided, you can download a free copy of the book. And if you have questions at the end of the talk, I have 2 printed copies here. You can get those. So in this talk, we will look at 2 things. We will look at how application architecture is evolving over the years, and also we will look at the infrastructure. How is the infrastructure changing from on-premise to cloud and whatever is coming next? So it will be a bit a high-level overview of application architectures, cloud architectures, and where Dapr fits. So let's get started. So I want to start first with the early cloud, pre-cloud era. So that's in the timeline I look at. This is the time before microservices, the time before cloud. And if you were a developer at the time, 2000 and 2010, if you were developing a reasonably complex application, maybe you were using something like an ESB, Enterprise Service Bus, to develop your application. And in addition to implementing your business logic, which is your core job, but you also had to take care of other things. For example, you had to take care of packaging your application, making sure it's placed on the right node, that it can make sure it deploys properly, so the old version is stopped, the new one starts, etc. Such an application would also do, networking calls, and in your Java application, you had to do things such as maybe use Netflix OSS libraries like Hystrix to do reliable service invocation, to do, mutual TLS, etc. Other things you have to do at the time in your application was asynchronous interactions, maybe using message brokers such as ActiveMQ, RabbitMQ, if you've been using those, do content-based routing, filtering, have connectors to different systems, and lastly, do stateful service orchestration. Maybe you have to coordinate how a service writes to 2 other endpoints. Do things such as, idempotency, distributed transaction, etc. So basically, these were all the different kind of responsibilities you had to do within your application. And for the infrastructure, as a developer at the time, I would have very little expectation from the infrastructure. I would see it almost like a thin layer. I would get compute like a VM with certain capacity, networking with static IPs, and some kind of storage like a file system and the relational database, and that's it. And what about the boundary between the application and the infrastructure, the boundary between developers and the operations team? I would say the boundary, the interface was in the form of, operating system primitives. That would be VM that the ops team gives you, or maybe there is also Java installed on top of that. Maybe there is some kind of runtime, like an application service, and that's it. There were no application-focused boundary. Now, this is kind of the structure I will use in this talk, just to see how the different responsibilities that the developers have to do and the infrastructure team have to do has been changing, over the years. And maybe we'll see where this is heading, maybe we'll see what's the tendency. Now, while this was the state of the art, before 2010, there were a few important ideas and influences that change the way we develop applications. But before talking about application architecture, we just have to agree on what we're going to use to visualize that. There are different ways to visualize software architecture. There is the 4+1 model, which uses a physical view, logical view, process view, etc. But that's not used so much any longer. There is more practical way to visualizing software architecture. It's called 4C or C4 by Simon Brown, which takes a more hierarchical approach for visualizing software architecture. It has things such as system context, containers that make up the system, then components that make up containers and the code. But for this talk, I want to take even a simpler approach. I just want to look into the applications from these two views, internal and external architecture, or internal and external views. And you can think of the internal architecture almost like everything that is within the developer's control. So these are all the functions and classes you are writing, the packages, the different layers, or everything that you put in a container, and everything that's treated like a black box from the operations team. So that's the internal architecture. And external architecture, that's everything that your service interacts with. So that's other services, message broker, storage, external endpoints, etc. So with this classification, let's see a few of the important ideas that changed the monolithic applications, right? The first one I would say is domain-driven design. A term coined by Eric Evans in 2003 in his book with the same title. And in a nutshell, domain-driven design is a set of principles that helps developers to encapsulate complex business logic and express that in a code. And domain-driven design, it introduced few important ideas. For example, it introduced the idea of a bounded context, which is a space where all the terminology is agreed consistently among all participants. It introduced the idea of aggregates, and aggregates a collection of objects that can be treated as the same from transactional point of view, so that they all share the same transaction boundary. Even though domain-driven design was created nearly a decade before microservices, it basically set the foundation and it became a cornerstone for microservices later. It helped developers to identify the right microservices boundaries. The next influential idea, in my view, is hexagonal architecture. So hexagonal architecture is a term coined by Alistair Cockburn in attempt to address some of the limitations of three-tier applications at the time. So if you are writing, three-tier application using Java and object-oriented, you may have cases where some of your business logic is leaking into the user interface. So hexagonal architecture introduced certain rules that help you identify the responsibilities between the different layers of within the application, and it allows you to encapsulate external endpoints from your business logic, right? And that approach is actually called ports and adapters, which is the other name for this methodology. Then we'll continue looking into these timelines going forward. Then there was onion architecture and clean architecture by Uncle Bob, which had a similar ideas. They keep introducing new principles and ideas how to separate the responsibility between the different layers you have with your application. In 2012, we got microservices and 12-factor apps. Built on top of the ideas of domain-driven design and 12-factor apps, basically microservices introduced new principles that let you identify the right boundaries of services that can be independently scaled and developed by a single team. And 12-factor apps, they introduced 12 principles that let you write more scalable cloud applications. Basically, these ideas, you see, they kind of evolve over the years. They build on top of each other. But as a result of that, the monolithic applications we have before that basically start transitioning into independent, smaller services. While the developers were trying to identify how to strangle a monolith or what's the good size for a microservice, let's see what happened with the infrastructure layer at the time, right? So what we've seen so far was what's happening at the application layer, but now let's look at the infrastructure a bit. Driven by all of these changes, and transition from monolith to microservice, we start seeing the emergence of new set of middleware projects that are specially created for distributed applications. Projects such as Apache Camel and Spring integration, they help you create distributed application and do synchronous call between the services or asynchronous interactions. Redis is a key value store which started around when the microservices were created. Apache Kafka helps you to do asynchronous publish, subscribe between your services. Camunda, Cadence, and Conductor, these are open source projects that help you orchestrate interaction between services in a stateful way. So this basically represents how some of the responsibilities from the monolith applications start shifting separately. But these projects still would be owned by the developer team. They would be self-managed. They wouldn't be consumed as a cloud service. I think what's interesting for me is what happened at the infrastructure layer. That's with the blue boxes, right? So Kubernetes, first Docker was announced in 2013, which basically started a huge wave of innovation in the compute abstraction and operational practices. Kubernetes and Lambda a year later, and a number of service mesh projects after that, which all that meant that the stuff you have to do within your application at the beginning, such as placing a service, starting it up, deploying, scaling, configuration management. Now you don't have to do this as a developer from within your application. Instead, all that starts shifting down to the platform level and become managed by the operations team. Similarly, networking interactions, rather than using something like Netflix historic library or some kind of HTTP client that can do retries, that can do, traffic encryption, you now can offload all of that to some kind of service mesh technology and handle it at the platform level by the operations team. Not only that, these platforms now are also moving to the cloud, so you don't have to manage your service mesh or Kubernetes. You can consume that from a cloud service. That means you as a developer have less things to focus, right? The boundaries have shifted also up. Now you as a developer, you can use a container as a ubiquitous format when you're passing an application to ops team. You can use a Kubernetes format to describe how the application should be scaled. And using the same language, using the same tool between developers and ops actually enabled practices such as DevOps, GitOps, and enables better collaboration. Now, I want to look a little bit deeper. If you are using containers to run an application, whether you are running that on top of container service, or whether you are running that on top of Kubernetes, or maybe even if you are using something like Amazon Lambda, there are certain coupling between your service and the compute platform. There's certain kind of interaction between those. These interactions are in the form of API interaction. These are in the form of configurations and even practices such as rolling deployment. So let's look at what's the coupling that potentially can prevent the portability of your application among different platforms. So let's say I have some kind of application, it has its own logic, it runs in a container, and I want to run that on a compute platform, Kubernetes, Lambda, or whatever you're using. So what are the couplings between those? First, I would say you have to tell to that platform how much resources your application will need, right? How much CPU and memory. On Kubernetes, you do that by specifying request memory and CPU request and limits. On Amazon Lambda, you do that by selecting how much memory your function will need. Then you have to tell the platform where should your application run, right? On Kubernetes, you do that with taints, tolerations, affinity, anti-affinity rules. On Amazon Lambda, you select a region and maybe you tell it whether it should run at the edge or not. Then you have to tell your to the platform how to check the health of your application. These are the various health probes Kubernetes can perform on your application to decide if it's healthy or not. Similarly, on Lambda can check the response of a function and decide whether it was successful or not. And if it's not successful, it will retry the request to your Lambda function. Then there are lifecycle events. For example, when your application is starting or when it's shutting down, the platform can emit events. And if you are interested as a developer, you can react to those events. There are similar events in Lambda as well. And all of these compute platforms, they also catch logs and metrics from your application and expose that. Now, the good thing is, if you are a developer, there is not so much for you to do. As long as your application is properly containerized and as long as you are implementing some health probes, most of these contracts and binding between the application and the compute platform, they are used by the ops team at runtime to operate your application, right? And most of this contract between the application and the platform, it is implemented using open source standards, whether that's containers, Kubernetes, Prometheus, JSON for logging, etc., etc. So that represents the coupling between the application and the platform. Let's look at then what's application external architecture, right? So we said compute binding is between the application and the runtime, but then everything your application is interacting with, other services, other applications, that represents your application's external architecture. So let's see what kind of coupling is there. I have, again, my application right now. It's running on some kind of compute platform. But in this case, I'm not interested in the interaction between the application and the compute platform. I am interested in the interaction between the application and everything else, right? That application, for example, you may need to have some kind of connectors. If your application is sending SMS with Twilio, or you want to pull some tweets from Twitter, etc. So you would need to have connectors for your application. That application may need to talk to other services with synchronous interactions, whether that's over HTTP and gRPC. You need this kind of connectors. You may have asynchronous interactions, as we said, whether that's a messaging or something like Kafka. They can be stateful interactions. If you're implementing something like a Saga pattern, right, when you have to coordinate interaction between multiple services, etc. So all of these represents the external architecture and integration bindings, the way I describe it. Now, what's more interesting here is how you can implement these integration bindings. The traditional approach is to have all of that within your application, right? For example, you can do that by embedding the integration libraries in your application. You can do that by adding, Camel, for example, into your Java application, or if you're using Spring, you can add Spring integration. You can use some of the Netflix open source libraries if they are still maintained. But these libraries are only available in few languages. Java is one of the lucky ecosystems because it has lots of open source projects that can do that. You cannot use those libraries if, for example, you are using a Python or something else, or JavaScript. And these libraries, they may not work in every runtime, right? They work with Spring and Quarkus, but if you want to use something else, you may have challenges. And the other thing is, when you are embedding these libraries in your application, you are coupling the lifecycle of these libraries in your application. So these libraries, typically, they have lots of connectors, lots of external dependencies. And if there is some kind of CVE in this library, you have to recompile your application, run all the tests, and redeploy it again. So there is certain coupling of the lifecycle. The other extreme of the spectrum is to use something like a cloud service. For example, you can use Amazon, EventBridge. There are equivalent services from Google and Microsoft. But the point is, you now import your integration logic into the cloud service, and you are coupling yourself with the cloud service. That means every time the cloud provider changes their terms or upgrades the service, you're coupled to that, and you're coupled to their ecosystem. Now you have to use their build tools, their IDs, etc. I would say there is kind of middle ground where you can use open source projects that are becoming almost like a de facto standard. They are not official standard, but because they are adopted so widely, they become something like a standard. For example, you can use Kafka for PubSub. You can use Redis for key value access, or the S3 API to interact with the file system. But one challenge with these projects is that they are very much focused on accessing a storage, or they are focused on one domain only, right? If you need something that has a little bit bigger spectrum, this way you can use Dapr. So finally, what is Dapr? Say Dapr is a project that was created at Microsoft initially. In 2021, it was donated to CNCF, so now it's not Microsoft technology, it's in CNCF. And basically, Dapr has a set of APIs for different distributed system capabilities. So, for example, there is a state store API, you see at the top, and that state store API is similar to the Redis API. So if you are doing key value access, you can use the Dapr State Store API. There is a PubSub API, which is similar to the Kafka API, right? But instead of using Kafka, you can use Kafka, or you can use Redis, ActiveMQ, RabbitMQ, or Cloud Service. Similarly, for the state store, you can use Redis, but you can also use some other key value store. So you can swap the implementation without changing the application itself. There are connectors. They are called bindings and triggers. So if you want to connect to some kind of API, third-party endpoint, you can use these bindings. And this list of APIs is growing, right? There is a distributed log API, workflow API. There is the API to access configurations. For example, if you are accessing configurations from Kubernetes, or if you are accessing configurations using something from the Spring ecosystem or a cloud ecosystem, you can use the Dapr API to access any kind of configurations or secrets. In terms of architecture, Dapr is not a library that you add into your application. Instead, it's a sidecar. It's a separate process that runs next to your application. That means from your application, you can call the sidecar, for example, using HTTP or gRPC. If you don't want to have any kind of dependency to Dapr in your application, you can use HTTP in your language, whatever is that, in your runtime, and you can just do, an HTTP call to the Dapr API, and Dapr will do the connection to some other systems and add, lots of other benefits. Or if you want to do you want to use an SDK, there is an SDK for all these languages you see on the screen, and that will make it easy for you to interact with Dapr, and it will use gRPC behind the scenes, so it's also more performant. Let's see a few examples how you interact with Dapr. So one of the Dapr API is called service invocation. So you can think of that as an HTTP client to some other services, or something like a service mesh. It does basically the same job. In this example, what I have is service A is trying to call service B, right? But rather than calling directly service B, in your service, you always call the sidecar, which is on your local host and a specific port. Invoke is actually the service invocation API, and then you tell the name of the other service you want to call. In this case, in the URL, you see it's an order service and the method you want to call and what data you are posting. So Dapr behind the scene will use some kind of service discovery mechanism. So if your application is running on Kubernetes, it will use Kubernetes service discovery. It is running on VM, it can use, for example, HashiCorp service discovery project, whatever is that. If it's on some other environment, it will use that. But Dapr will find the actual location of the other service. It will encrypt the traffic from this sidecar to the other one, and it will invoke the other sidecar. And then it will give you the result back. Now, why would you do that? I would say you get a number of other benefits. For example, service discovery is one. The other one is secure communication. So Dapr will automatically apply, MTLS between the sidecars. In addition, you can have additional security. You can tell which sidecar can call your application or which application can call the sidecar. So you can use tokens there. You can apply authentication and authorization. at the Dapr level, you can trace the calls, all of this service interaction, or you can apply resiliency policies. So they can be circuit breakers, retries, timeouts, etc. And you do all of that without changing your application. All your application is doing is calling the sidecar, and Dapr can add and change its behavior at runtime without changing your application. This was the service invocation API. There is the publish subscribe API. As I said, it's similar to, let's say, Kafka, but it's a broker agnostic, so you don't actually have any kind of Kafka clients in your application. Instead, your application is calling, you see at the bottom, publish API. It's publishing a message to the order topic. And on the other side, the other sidecars, they have to subscribe to that topic, again, using the sidecar. Once you do that, you can actually swap the implementation of your broker provider. For example, locally, you can use something like Redis, but when you deploy on Amazon, that can be swapped to use Amazon SNS or SQS. If you deploy to some other cloud provider, you can swap that without changing your application. In addition, just to PubSub, it has additional features that you may not have in the client of your choice. For example, if you are using Kafka, maybe there is not a filtering and routing. In Dapr, you get that. You get additional retries, dead letter queues, bulk operation, where Dapr can aggregate multiple messages and send them at once, or the other way around. It can consume multiple messages, aggregate them, and pass to your application. You can set time to live, you can scope topics to specific applications, and you do that regardless whether the actual broker support these features or not. The other API, state management, I mentioned earlier. This is probably one of the simplest one. It is similar to Redis, which means you can do key value manipulation, right? At the top request, you see you're posting a key value to specific order store topic, and with the bottom, with the get request from the sidecar, you're getting that. It supports, as you can expect, all the CRUD operations, but you can also do bulk operations, so you can query multiple values at once or send multiple values. What you get here is that in addition to the traditional just the key value access, you can actually apply, for example, encryption of the data, right? Dapr will get the request from you, will encrypt the data, and then it will store it in the actual state store. And again, when you are reading, it can do the decryption for you. So it abstracts the key value access stores and adds additional capabilities. And the last one in the APIs is the bindings. So bindings are connectors. In this example, we have an application that is trying to send a message using Twilio. But rather than having a Twilio client library in your application, what the application is doing is the application is only calling the sidecar, the binding API, and Twilio, and Dapr makes sure that that message uses the Twilio client to send the message, right? This way, you keep your code clean of all of the external libraries, and you still get all the benefits, right? If there is something wrong, Dapr can retry these calls. You get tracing, security, etc. This binding is a type of output binding, which means it goes from your application to an external store. Then there are also input bindings. Input binding is when your application is trying to get some kind of data from an external endpoint, right? In this example, maybe you want to poll Twitter API and get the tweets, right? Rather than having Twitter Java library in your application, Dapr can do that. And when there is a new tweet that matches your criteria, Dapr will call your application. In this case, Dapr will do a post request to your application that's running to the new tweet endpoint and will pass you the content of the tweet. So if I were to summarize, all of the Dapr benefits, I would say, it has benefits to architects, developer, and ops. And as an architect, if you are working, in a big organization with multiple teams that maybe they are using different languages, not all teams are using Java, right? Maybe there is a data science team that's using Python, maybe the team that's using Microsoft technologies, .NET, and there might be new projects that are using Node.js. As an enterprise architect, if you have Dapr in your organization, now you can make assumptions that all teams, they have certain capabilities, all right, without knowing the details, what's the exact language that team is going to use, what's the runtime they are using. Also, you have deployment optionality. So when you create a service with Dapr, that can run on a VM or locally, but it can also run on different cloud endpoints. When you run a service on a cloud provider, that service also has to connect to the different cloud services, right? So it's not just running, but you also have to consume things such as messages, interact with the other services. So Dapr connectors can easily swap those. You also get knowledge portability, which means these enterprise integration patterns, these distributed system patterns, they become you can take them with you when you're going to another team, when you're going to another employer, right? You are not kind of so narrowly specialized. You have something that you can take with you. And in my view, the most important one is probably maintainability. If you have to upgrade an application with Dapr, you just change the Dapr version and you restart your application. You don't have to compile your application and run the test, because the interaction between your application and Dapr is purely based on API interactions and contracts. So it makes upgrades much less painful than if you have to upgrade or refactor an existing application. For developers, as I said, these are all the benefits I just listed. These are a set of APIs, and this list is growing. For example, in the latest version, Dapr added stateful workflows. That means now Dapr can do coordination between your services. So Dapr can call one service, it can call the second one. If the second one fails, it can roll back and call the first one again. So stateful orchestration like a business process. There are proposals for new APIs, for example, things such as change data capture or document access, etc., etc. So you as a developer, when you are implementing your services, you can use Dapr. And then once the service is using Dapr at runtime, now the ops team they get enhanced visibility to all the interactions. They can configure actually behind the scene what is the actual database, broker, or cloud service Dapr should connect, because that also has to be configured, and that's typically done by ops team. So they get visibility, security, and reliability in day two. And that's kind of summary of all the benefits. I just want to give you one highlight of how the project is doing. So it's a project in the CNCF, where Kubernetes is. It has, over 20,000 stars and over 2,000 contributors. It's been growing very rapidly, and we have actually, users from Turkey as well, a number of users. This was a quick summary of what Dapr is. So my suggestion is, if you find it interesting, go have a look. This brings us to the last section. So if we were to summarize what happened is, in the application layer, we've seen that big monolithic applications, they are basically becoming smaller and becoming fully created by independent components. And the infrastructure layer, the infrastructure is moving from on-premise to cloud, right? If we look at the runtime responsibilities now, I would say they are mostly done by the operations team. You as a developer, you still write some kind of business logic. Maybe you put that in a container, but the way it runs is an operational concern. And these operational services, they are also becoming specially suited for applications. What I mean by that is, instead of, for example, on Amazon, instead of creating an EC2 instance and then installing Kubernetes on top, you can directly use Kubernetes as a service. Actually, you can go a step further. Instead of using Kubernetes as a service, you can use a container as a service. So you can use, Fargate and AppRunner, which are services that run exactly one application, and it's serverless and it scales automatically. On the networking side, on the synchronous interactions, rather than using something like Elastic Load Balancer at the TCP layer, you can use Amazon API Gateway, which is at the HTTP layer, and where you can apply additional some kind of filtering logic, etc. On the asynchronous interaction, rather than using EC2 and installing Kafka, you can use a topic as a service or event bridge as a service and configure your application. And the same with the stateful interactions. And this is the last slide. So if you want to create, let's say, if you're wondering what does this mean, if you want to create more portable applications, I think there are 3 takeaways from here. First, when you are designing your application, you can apply some of the knowledge from domain-driven design, some of the microservices principles, hexagonal architecture, and find the right boundary for your service. And that maybe your service has to be a function, maybe it's a microservice, maybe it's monolith, that's all fine, but you have to find the right boundary. Then second one is look at how your service is going to run, right? These are the runtime bindings. So here, if you're using something like containers to package your application, if you are using Kubernetes, if you know how Kubernetes works, all different kind of health probes, etc., probably you will know how to run that container on different kind of cloud services. If you are using OpenTelemetry to export metrics, if you are writing logs into JSON format, probably that's a very, very good start, and that will make your application portable. Then on the integration side, try to pick up projects and APIs that are open and portable. So you can use things such as Kafka, you can use cloud events for the format of the data, Redis API, or Dapr APIs to wrap your application. And I think if you do this kind of 3 things, your application will be portable across different environments and across different, your skills will be portable across different projects and employers. That's basically the summary, and that is basically focus on the business logic and try to reuse everything else as a cloud service if you can. When you're doing that, try to use open protocols, open APIs, which make them portable. And when I say portable, it's not portability of the application, but more portability of your skills, right? If you run these open source projects, you will have skills that you can apply different projects and different places. That's all I have. So if you want to create a free copy of the book, which is sponsored by Red Hat, you can get it from that URL. Otherwise, if you have questions, I'm here to stay. And I have a few stickers and 2 books to give for good questions. Thank you.